Okay guys, let's get started. So as you can see, we're slowly moving through. We've now done our first week. We talked a little bit about the tools. The second lesson was basically how to organize the problem and understanding the problem. Third lecture set was for UML. We then discussed functions, how we do functions to doing each part of the program. And now, finally, now we are starting to implement things using variables. So this was a 3-week session for variables, and the key lecture was last week. So now we are basically moving on from the key ideas that we learned last week to try to figure out how to do things. So last week, we discussed going from the various, from your commented code or your pseudocode, going into code using variables that actually do the work. So for today's lecture, we are going to be, opened the wrong. Okay, so for today's lecture, we will be working on variables, the last one for variables. So our outline for today will be as follows. Okay, so the first lesson we worked through this. Today's lesson will be going through and taking up your homework first for the variable analysis. Then we'll discuss the need for a coordinate system for the OPIX program, and we'll also talk a little bit about root finding. We will then give you a chance to modify the OPIX code to solve this problem for the coordinate system, and we'll also talk about some other information, a little bit other stuff on the root finding stuff. Okay, we will then take a break, and we'll take up the code you actually did write for modifying the coordinate systems, and then we'll start moving into pointers, introducing pointers. I just sort of a heads up. We're not going to do a lot of work on pointers today, but I'd like you to have a heads up for what will start after the midterm. After the break, we'll then give you milestone 2, UML try 4, milestone 3, try 1. Sorry, not UML, milestone 3, coding try 1. And you'll have a chance to try the milestone, and then we'll spend some time walking through the solutions for these 2 milestones. I think the UML will be quick to walk through, and then we'll show you how we've walked through the coding for the other one. Okay, so we'll try to walk through some solutions, and then finally we'll go home. Next week will be the midterm. For 2 to 3 o'clock will be retry for milestone 1. 3 to 4 will be retry for milestone 2 from 2 to 2:30. Then we would take it up, and then the third hour will be the try for milestone 3, assuming you passed milestone 2. Okay, so that the half hour will give us a chance to mark your milestone 2 in the second half of this hour. Okay, so if you pass all 3 milestones by today, you do not need to come next week. All right, okay, so that's basically what we'll be doing to do. That's our objects for today. So let's start to look at the different applications. Okay, the first one, we're going to walk through the 3 solutions going from COM to variable. We looked through the gravity one last week, so I just want to working through the OPIX program and your homework, the root finding program. And then we'll move on to coordinate systems and rule breaking. Okay, so let's look at variables first. Okay, optical ray tracing, implementation of our pseudocode in ANSI C. Okay, this was a pseudocode that we had created, O0COM pseudocode, and in that pseudocode we had a prototype for I, prototype for H. We called get flow prompt, we called something to get I and H, etc. Okay, so then we moved to write some C code. This basically being the C code we end up getting out. We have our prototype for our equation lens. We have the prototype for the magnification. We have a calls, and we have the magnification and then the printing. This time I'm just using Git, this one is just using Git float. It's not been updated to Git float prompt yet. Okay, so equation lens and then magnification. Okay, so let's walk through it. Okay, so here's the actual updated. Okay, so we compiled it, and you compiled it, and then you ran this code. I hope that's what we should have done last week. So let's walk through it now. First of all, the first 2 lines are for information for humans. The computer doesn't care whether you write it or not, but I suggest you write the program name, what it's doing, your author's name, and when you wrote it. The next ones are function prototypes. Okay, this is the standard where the function prototype for fprintf is going to be. This is the function prototype for Git float prompt. Then we have the function prototypes that I've written in this file, my own functions, equation lens and cmag. So I'm telling the program, you'll find the 2 function prototypes right at the bottom of this file. You'll be able to find the definitions here. Okay, main then starts. So again, we're going to analyze with variable pointer diagrams. Main starts, then we declare containers. A container double with O, a container double to hold I, a container double to hold F, and a container double that's holding H. Now H, I'm already automatically initializing it at 1 to make it simple. So an image height of 1, and it's stored as a floating point number, so which means it's stored in 2 halves. A 1 in one bin, and an e to the 1, and a 1 in the other one to say how do you move the decimal place. Okay? Or the radix, to be exact. I then call Git float prompt, and input my, for example, 2 as the position of the object distance, the focal length of the lens, the distance between the lens and the object, as 5. I call equation lens. Okay, when equation lens is called, it copies 2 from container O of main to container O of equation lens. These are not connected. This is a copy. Then I copy from container LF or F of main into container F of the lens. Okay, so that copied. Now when the control is now transferred to equation lens down here, we keep marking our spot, but the control now jumps down to equation lens, the function. We enter the function, and the first thing we do there is to create a container and give it the name I. We then take the values from this line, takes the value from container F, and takes the value from container O, multiplies them together, then takes the value from container O and subtracts the value that's in container F, and places the final result into container I. In this case, minus 0.330, e to the 1, so 3.3. This is then returned to the main program at this point. Okay. Once it's been returned to the main program, we come back to the next line, and the program continues. Okay, cmag is then called. Copies are made again. 0.2 is copied into the magnification program. Minus 0.33 is copied into the magnification program. The I position. It's copied into the magnification program. It then creates a variable, a container M, again of type floating point container M. Then it takes the value in container I and the value in container O, dividing them and putting them and doing a negative sign to give us 0.165. And finally, it returns M to the main program. M is returned to the main program, and you can see here this special H times. So this says take the value M, multiply it by H, which was 1, and put it back into container H. Okay, this is a short form for multiply and put into a container. Okay, so this is short form. If I want to check, I should probably show that very clearly so you understand exactly what is happening there. Okay, moving across. So Notepad, what actually is happening here, it's going, get rid of this. Okay, C, H equals C mag, what is it, I comma O, I think we have here. Yeah, O comma I, O comma I times H. Okay, so take the value and calculate this. This guy, so this would be what the code looks like. What actually happens is, first of all, I called C mag O.H and got the value of M. So this becomes H equals M times H. So take the value in container M, multiply it by the value in container H, put it back into container H. Okay, we simplify this whole equation by just writing H times equals C mag 0 comma I, which I think is a short form both for this and probably Python also can use this short form. All right, for doing multiplication and storing in the container. Taking out of a container, storing, but it actually should be expanded to this. So when the computer runs, it actually expands it to this for the computer, okay? So this expands to this. All right, let's move back to what we were talking about. So we have 0.65 comes back. And now we call fprintf. So I'm printing two things. So I give it the value in this container is given to fprintf. The value that's in the container H is passed to fprintf. And I tell fprintf to print it to standard output and use this format. Okay. And we can see here that printing it out is printed like this. Minus 3.3000 equals 1.650000. By default, we always print 6 decimal places. Okay? By default, C will print 6 decimal places. All right, and then we return 0, main returns, and that's the end. Okay, and once main returns, these values are just left in memory after the code ends, and whoever has the next program will find them in that memory. Okay, that's our first one to look at. The next one I want to go through is R3com. This one I would like us just to, I'll walk through it, and then we'll run through the code, okay? So that Control C. Where's my notepad? Notepad. Oh, I closed it already. Sorry, okay. Okay. File, save as. Back saving it into, not documents. Where's our directory? This PC, local disk, SDBA. Let's give it a name, I don't know, j.c, nice and simple. Okay, all right, so here I need a prototype. Okay, I already have here, so let's just, I'm going to get rid, as I work through it, okay, I'm going to get rid of these extra comments that I don't want anymore. And, okay, my first prototype, so I'm going to return a type double. I have to make that decision, double or fixed. C mean. I'm going to decide that I'm going to use the first number I'm giving, I'm going to make it type double. The second number I deem I have to make type double. So I have to decide whether I want to use fixed point or floating point at this time. And I think I'll just use floating point for everything. And this next line, I'm going to replace the proto with double y equals equation of double x double p. Now, I guess I could choose fixed point p because I'm doing the square root of 2, square root of 3. But I think I'd rather keep everything as double. Make it simple for me. Okay, so now I say I'm using get float. Okay, what variables am I going to need? I'm going to need xs, xb, x, and p, and a y. Okay, so I'm going to have to get all these guys out. I'm going to make doubles. Double xs, xb, x, y. I think that's everything. I only have 4 variables, so x s equals get, okay, I'm going to guess get float prompt, and my prompt is decide what sort of prompt I would like. I can choose my own prompt. I'm going to say input value of x smaller than expected root. Okay, and what's my next value? Okay, it's next going to be xb, and I can decide what sort of prompt I want. Maybe I just put input value of x greater than expected root. Okay, and okay, I've input x, I'm going to calculate y. I could also put a p too if I want. Okay, let's put a p here this time. P equals get float prompt input number for which you want square root. Okay, and that's probably everything I need. Next, I'm going to calculate x. So I just have to use this function. Nothing exciting. Since I already have it, what I'm going to call it, I will call the function. I can now change this guy, just get rid of the comments, call this function. And now I have to write an fprintf. Fprintf, where do I want to print it? I think I'll print it to the monitor. And I'm going to, how do I want to make it look like? Okay, maybe I'll put, okay, x equals %lf, y equals %lf. That should be okay. Tell me what I'm outputting, and that's x, comma, y, and maybe okay, all right, that basically completes my main program. All right, and let's save it. Okay. Now I need my definitions. Okay, I can copy these. Let's copy the 2 function prototypes first of all down. CMean and equation. Okay, I'm going to copy CMean down here, and it's going to be a definition. I'm going to put a definition for this guy there so I remember what I'm doing. For this guy, I need to input x and p. My formula, I need to create a new variable, double y. And so formula is y equals x times x minus p. and I'm going to want to return the value of y. There's my equation. Next, I can get rid of my comments now. This will be another one, the mean. Do I need a new variable? Yes, I need an x as my new variable. So double x, and I can write, and this divided here, and then I'm going to return x. Okay, I've now written my first version of the code. Now it's time to start to see what have I done wrong, which there will be stuff wrong, as always, but we're going to look to see the error messages now. This PC, local disk. So I will go to SDBA and NCC. More info, run anyway. Okay, come on over here. Thank you. I'm going to put you over to one side. Come on. There, I like you on that side, you on that side. Bigger, large. GCC minus C minus wall J.C. And we'll get a whole bunch of errors. Okay. It's telling me I've got an error here on my function on here. Whoa, lots of errors, tons of errors. Warning, implicit declaration of function mean. Warning, warning, warning. Okay. It does not like this double here, x equals. So I realize I should not have there. I should not have that. I should not have that. I should not have that. Okay? Pardon? What else don't I like? Line 8? Oh, I have a period here, okay? Good. So, fair enough. Save. Don't make too many changes. Don't look at too many errors. Correct one at a time. And we'll see what errors we get next time. Oh, no errors. Oh, okay. Minus O, J.exe, J.o, and remember I used JInLab, so I've got to have JInLab.o linked with it so I can find the for my input. Okay, and then J. Okay, input value of x smaller than root 1, input x greater than root 2, number I want the square root for 3. Okay, and it told me, okay, for x equals 1.5, y equals 0.75, so I know it's smaller. I could then run my program again. I know that. So it's smaller than root 1.5, greater than root 2, number for root 3. Okay, now I have greater, so I know it's somewhere between. Okay, so it's now 1.5, 1.75, right? So I ran it again, 1.5, 1.75, and okay, now it's negative, so I can start to, you can see I'm now moving in and narrowing in for my root. Okay, so let's now walk through this code. I will go back to my, where's my ANSI gone? Have I lost my ANSI? Yes, I have. Gone to my, oh, how did I do that? I didn't want to close that. Okay, never mind. Okay, we'll go back to ANSI. Index, somewhere down here. Tape modified. Index, here we are. Okay, so let's look at the next Okay, so let's walk through it now, and we see how the code runs. All right, from problem definition to solution. Okay, we went to pseudocode now. There was our pseudocode again that we just started with. And we wrote the ANSI C code. In this case, in the case when I did it this time, I hard-coded the 2.0. I did not bother typing it in. I decided to hard-code it, so I have one Lex variable, don't have P. I just hard-coded it. Okay? And that... Okay, so we then ran the code, and if necessary, you work on debugging it, which we just did. This is basically the same code that we just did here. All right, you can see everything looks the same, but now let's walk through it. Information for human beings, first couple of lines. Information for the preprocessor, where some of the function prototypes are going to be. More function prototypes for this file. Okay, and then we start again. Main starts. We declare our 4 containers, XBS, XB, X, and Y. I call get float prompt. In that case, I type in 1, and it gets stored into the memory location. Get float 2 prompts me with XB. I type in the 2. It gets stored into XB, container XB. The program then comes to call cmean. So it comes to here, control drops into function cmean. Cmean receives XS and puts it in container A. It receives the value in XB, container XB, puts it in container B. It then creates its own container X to do to store the calculation result. It then takes the value out of container A, takes the value out of container B, adds them together, divides it by 2, puts the value into container X. And then finally we return X to the main function. We move to the next line. We call equation, the function equation. Again, the main drops to one line. It calls function equation, transfers control to function equation, and it puts the value X, the value that's in X, that it just calculated, it puts it into X. It takes the value of 2, puts it into P, creates its own container Y, takes the value out of container X, squares, multiplies it by the value in container X a second time, multiplies them together, so then takes the value out of container P and subtracts it from this value, and finally puts it back into container Y. And then returns Y to the calling program. And disappears. Next step, it moves and prints, calls fprintf, which basically, using this format, okay, prints the value Y 1.5000 to 0.2500, so it hands this value into printf, which then prints it. And it returns to 0, and then that function ends, and then function main ends too, leaving stuff in memory that, whatever, which will be overwritten later. Okay, so we've now gone through these two guys. I want to now look at what we'll be doing next. I want to talk about, there's how we should write code. Okay, you see how our code should be. I'm going to talk a little bit about rule breaking, and then we'll move on to the next thing, okay? Breaking the rules, okay? There are ways in which we should do things, and there can be ways in which we do things that are not correct, but work still, right? Obviously, this is not the way you should get a cookie, but it works. You get the cookie, and you're happy and enjoyed it, even though you were not supposed to do that. Okay, all right, so this is the good way of doing it, okay? This is our root finding code, very nice. It For solving, our solution method is we do the hand coding, hand check to understand the problem, then we write a UML, then we do the C code. This is the way we should be progressing. Not doing the C code, then doing the UML, and then doing the hand calculation, as some people like to do. Don't. All right. For variables, we declare them. We initialize the variables. Like XS is initialized. So it's on the left-hand side. It appears on the left-hand side of the equation before it appears on the right-hand side. Okay? So you can see XS appears on the left-hand side, appears on the left-hand side. X, now XS and XB can appear on the right-hand side. And X is then appears on the left-hand side. Now, Y can be initialized, and X can appear on the right-hand side. So the variable should not appear on the right-hand side before it's been on the left-hand side. Okay? And once it's been on the right-hand side, it's initialized. Left-hand side, it's been initialized. Then we can use it. So for example, here I'm using XS and XB to calculate X, and now I'm using X to calculate Y. It has already been initialized and it was already declared. So X was declared, it was initialized, now it was used. Okay? Question? Question? Do you have a question over there? Please ask and I try to explain, because probably if you have a question, other people will probably have too. Okay? And finally, for functions, I have a function. You have a prototype, a call, and a definition. There's my prototypes. There's my calls in main, and here's my definitions. Now, do you have to do this? Well, no. You can start to break steps. For example, okay, here's the first one. This is not ideal. You can see what we've done here. The functions have been changed. What have we done? We have, first of all, shortened the code. It still works. There's no problem with the code. But we've skipped the prototype. You see there's no prototype. I put the definition at the front of the file. So C allows you to do that. If you put the definition first in your program, you don't have to write a prototype. Okay? But you won't be doing that in this course. You will be writing prototypes. Okay? What else have we done here? I have initialized, I declared it and initialized all in one step. I declared it and I declare it and initialize all in one step. XS and XB are initialized in one step. Thirdly, in this function, you can see in these functions I have not declared any variables. I just did the calculation in the return statement. So I got rid of the declaration of double X, I got rid of the calculation line and put it all in the return statement. This is nice and short, but if your program doesn't work, it will be very difficult to debug. Okay? Similarly here, I eliminated double Y, I eliminated a variable, I just returned this value without storing it in a variable container, without storing it. Okay? And finally, look at this. In the function call, I have added function calls. Okay? So now I'm just calling CMean here, I'm calling equation, and I'm calling the two, all in the function call. Okay? So this function call is actually doing a bunch of calculations together. Equation is taking a CMean. It's doing this. So this equation is calling CMean. So fprintf is calling equation. Equation is calling CMean with the values calculated in mean. And this is very confusing. Okay? So please don't do this. But I can also break some more rules. let's go from this guy. It's still understandable. I can still understand this code. It takes a little bit of time, but I can still understand what's going on. Now I can start making it more understandable. Okay? I take this code, which I don't like you doing. I can now break it down here, double X, double B. Instead of giving any, I can write it as fscanf, standard in, %lf, address of xs, xb, and then printf, %lf, ss over 2, xs over 2, no more functions. Everything in the main code pretty well. I reduced the functions, okay? So functions, main is being used for all user code. So there's really no explanation of what's going on. For input, I'm using standard input library fscanf. Now, the problem with doing it this way is there's no error checking. And there's no user prompts being given. So the user doesn't know what to input and what format to input. If the user doesn't input two numbers separated by a comma, your program will crash and not run. Plus, the user doesn't know whether he's supposed to put in the small number first or the big number second. There's no information, and there's no checking to see if he actually does it, or types some characters or something. Output, I'm using printf. I'm now assuming I want to use the operating system's default always. I'm assuming I will never need to output this data anywhere else. I will never need to output to a file or anything like that. I'm just assuming I always want to put to the monitor. And you can see I give no information about what the information I'm outputting is, so the user can guess what the output is. I've got no labels. Let the user guess. Who cares? He can guess what the numbers are. Okay, not good. But let's continue to break a few more rules. This is something, okay, note, I'm using one more rule breaking. I'm writing 2. I'm not writing 2.0. 2 means I'm using a fixed point number 2. I'm not using a floating point number 2.0. And I'm hoping the compiler realizes I want to use a floating point number. Because obviously dividing, if it does integer division, I'm going to get the wrong numbers. So I'm assuming the compiler knows I want to use float and not an integer. Again, in this case, the compiler will guess correctly, but it may not always guess correctly. Okay? So it's better to tell specifically. Okay, next rule breaking. Let's skip comments. They're a waste of time. Okay, let's confuse the readers. Forget about what comments. Don't tell the person what this program is supposed to be doing. Skip the comments. Variables. Oh, XSSB, why bother? Just call it IJ. Just meaningless names for the variables. Call them anything you want. One letter is faster to write, right? Just typing any letter. And I'm using I and J. In computer programming, I and J is usually used for integers, fixed point numbers. So by doing this, I'm really confusing anybody trying to read this code who's used to C code or Python coding, because we always use I and J for counters, for adding 1, 2, 3, 4, 5. We never use it as a double. You will never see anybody using I and J for a double. That's standard operating procedure. It's not a rule, it's a standard operating procedure. Okay. All right, protocol, or we could call protocol. All right, but why stop here? Let's make it even more troublesome, our code. Okay. I've broken this. C also allows you to put everything on one line. You don't have to use more than one line when you're coding. You can put everything on one line. Integer main, return 0. Okay? Great. And I can skip the void here. You can see I'm skipping the void here, saying I don't need anything. C will guess that you don't want to give anything. So again, I'm allowing C to do the guessing. Okay? But I now jammed everything into one simple line. Okay? And put your whole code on one line. That makes it even more troublesome for anybody trying to scan through it. Try that in Python, you can't do it. Python won't let you do something like this. C will let you do it, but Python will not. Python will basically not let you do this, so something you can't do in Python, yay. Make it so confusing. All right, so please, let's follow the rules. Declare, initialize, use, prototype call definitions, use functions to do what you're doing, make your code clear and readable for people who are coming to look at it. Okay, we will now take a short break and then we're going to move into the necessity for coordinate systems. So let's break now for 10 minutes and we'll continue on with coordinate systems. All right? Okay, we'll break for 10 minutes. Okay, so we're clear. Okay, so let's start to look through these issues. So our first program works for optical ray tracing, but it's not going to be, it's got problems. Okay, let's look at what we're going to have to do. So we want to handle multiple lenses. So we're going to need a coordinate system to add to this system. So we're going to have to modify the program to do add a coordinate system. And you'll be able, we're looking at, in our book, we should be on page, what page are we on? Let's see, page 39, I think, right? 39? Not this book, 39. Correct? 39, I hope. Where did my other guy go? 39. Okay. So on optical ray tracing, page 39, right? Okay, let's check. Make sure I'm at the right spot. You guys are all at the right spot. Yep. Coordinate system, section 4. Okay. We're going to work on trying to do the coordinate system with a hand. First of all, it's going to hand calculation. I'm going to show you it. Then we're going to work on trying to do a UML for it. You can draw your new UML here. And then we will write pseudocode in COM2 and then fill in the table. All right, so that's what we're going to do for this next hour. Okay, let's walk through together what we're going to be doing. Okay, so this is what we have so far, right? We're inputting the object position. We have a simple lens and we have a focal length of the lens. And we're inputting we have the height of the object, how far the object is from the lens, the focal length of the lens, and we want to calculate where the image is going to be formed at the other side, which is going to be basically over here. It's where all these rays will coming from the top, where they're all going to combine again. So this is the point we want to find, I, and in our equation here we said I equals OF, O minus F is the formula. HI is going to be equal to minus I over O times HO. This is what we started with. And then we were just outputting IX and IH. Now that works very nicely for a single lens with the object on the left side, the image on the right side. Okay, but what happens if we have multiple lenses? It's going to be very difficult to keep track of where I and O and everything is going to be. So, therefore, we need to add some sort of a coordinate system. Like we can then say, okay, this person's at x0, the lens is at x1, the second lens is x2, and we're going to try to find x3, where is the person standing. So we basically add a coordinate system to give us flexibility. And now we can think of it this way. If I go back to one lens, I can say, okay, here's the initial object position, here's the lens position, so plus O is going to be the distance between x1 minus xO is going to give me O, right? If I have the coordinate x1, I subtract xO, that will give me O that I need for my input. I could then use the F to do the calculation. F doesn't change. and that will give me I. I can then add I to x1, and that will give me x of the image. Okay, you can see how that's going to work from the diagram, right? If I know where the person is, I know where the lens is, I can then calculate the distance between the lens and the object. Once I have that, I can then calculate how far the image is away from the lens. And so I just have to add that image distance, x1 plus x plus I. That will give me the position of the image. Okay? So those are the two additional steps that I need. So let's go now to, so object, I can count x1 minus xo, and the image is going to be the position of the lens plus I that I get from this equation. And that will give me the actual position coordinate of my image position. And IH is the same, it's I over O. Okay, so if I go back to our UML, so in this case, if I'm doing multiple lenses, my last image will be the next object, right? So I'll trace it first lens, then that position will be where the object for the next lens to show. So I'm going to have to input the initial position, its height and distance, the lens position, its position, and the focal length. That would then calculate and output IX. So I'm going to have to add a few more steps now. I'm going to have to add a function to calculate this, to convert I, which is going to be O equals X lens minus X object, or X object minus X lens. Okay? And that will calculate my O. And the other one will be one to calculate IX, which is going to be XL plus XI. Okay, so I'm going to have to add those two extra lines into my code. Okay, so there's our basically our codes we're going to be entering. And the first thing now is to write pseudocode. So what I would like you, so what we're going to do now is take, starting from, so your starting code is going to be, if we go back to our programming language website, your starting code should be R4 O4 var.c, which I think should be right. Okay, it's the object for coordinates, what we want to get. Hang on, okay, O4, where is my O4? Where did I put him? I'm gonna have to, oops, I don't know if I put him up on, I only put him on in the PowerPoint. Okay, that's probably not, okay, that's, shoot, okay, O4 var, okay, I'll upload it I'll just upload it right now to you onto the website for you. It should be, I have it here, ANSI O4 var, just a sec, optic, O4 var, okay, he's not here either, okay, sorry about that, O4, we just did it, okay, O4 var, let's see, okay, sorry, okay, just a sec, I will get that for you, I apologize, I thought I had put it up there, but I did not link it yet, okay, okay, this guy I will need, oh, here it is, okay, oh, sorry, I did put it right here, there it is, so click here, no, oh, good grief. Okay, all right, let's just give me a second to get that done then, okay. I forgot to upload that, oh, good grief. Okay, just a minute, okay. Sorry. Okay. I will leave this guy up for you now. So you okay? That's R3 R. Oh. Okay. Let's just quickly generate it ourselves then. Okay. O3 com. Notepad. O3 com. Oh, come on, copy. Copy. Sorry, this will take a second. I apologize. Okay, there was our commented code from before. Let's just quickly write it. Double, okay, our prototypes. This was a double. So we decided we wanted equation length to return a double. We wanted CMag to return a double. If you want, if you have this already done, you could also take your own original code. This is double. Double. We'll use double for everything again. Finish our function prototypes. Double, okay, and we need to declare our variables, double F H O, okay, and then the get flow prompts, F equals get flow prompt, and we want to prompt F, okay, for F. We want to get flow prompt for H. Sorry, H equals, and we want to get flow prompt for O. O equals for our program to run, and then we need to call equation lens, which is series, okay, which means I also need the I, comma, I, okay, there we go, equation lens, and H times equals CMag OI, and then the fprintf call. Standard out, comma, I would probably, okay, let's percent LF, comma, percent LF, comma, percent LF, comma, percent LF. Okay, maybe I would like to put something like 2. I can put it whatever I like, okay, to add H equals percent LF. Okay, so maybe I want to put F, object position, image position, and H. Okay, I've only got 4 things there. Okay. Okay, and that's, I'm going to print that, return 0, create my definitions. This we're not going to change. We're going to keep these functions the same. We're not going to change any of these functions here. Maybe I'll initialize double I equals O minus F, return I. Okay, let's indent it so it looks nice. And we'll do the C magnification guy as well. Double M equals O minus O over I, and return M. Okay. I think this should be okay. Let's make sure it runs, and then after, assuming it runs, then I'll send this code to you guys. Okay, indent, make it nice. Save, okay. Let's go, okay, I need my prompt again. I don't want you. Okay, I don't want this guy. I want my NCC prompt. Local disk, this PC, local disk, SDBA, NCC, open, yes, okay, and GCC minus C minus wall j.c. Oops, function main, we have a problem. Okay, try to check it. Where's my notepad gone? Here we are. Notepad, there's a, okay, oops. Semicolon, semicolon. I should put this over here so you can see what I'm doing. Yeah, so semicolon, so it gave me semicolon expected, right? J10.2, 10.2, semicolon expected, that was missing, that was missing, that was missing. Okay, all right, let's try again. Okay, equation 1 of is undefined. Okay, multiplication sign needed. Save. Okay, compiles okay. GCC minus O j.exe j.o stamp John in live.o. Compile it. Oops. J spelled the library wrong. Good grief. Okay, J, okay, F, 4, H2, object 2, okay, good, okay, inputs, so its location is -4 is the image, H equals 1. Looks okay? All right, so how am I gonna be able to give this to you without it? Hopefully I can give it to you without the portal deciding to crash on me. Okay, so I will work on, okay, new tab, okay, and okay, portal, and okay, see. Maybe we try email. That might be easier. It might work this with email. I think maybe. Okay. All object code to modify. Okay. Oops. Object code to modify. See attached file. Choose file. SDPA j.c. Okay. Okay, so you should receive the file. You can now download the file and work on trying to do this to convert it. First of all, go through commented code and then try to write code that will actually do this. Okay, let's move to our, I'll go back, expand again. We want to go to write the pseudocode, make the changes that you need to add these extra functions so that we can now put in the pseudocode and modify it so that we have pseudocode first to do the functions and then move on to writing C code that will actually do that. So where you need to put the new functions in and where you need to put the old functions in modifying our current code. Okay, and you have a UML here to draw in your picture. Okay? Okay, let's come back and we'll walk through together. Okay, we're going to walk through together. You can think about what your code. So I will move to here and let's walk through the solution together. Okay, let's start. We'll walk through. Okay, so I need to add, first thing I can see here, I'm still getting H and I'm still getting F. I'm calculating O. So that means I'm also going to need to get an OX equals get flow prompt. And I'll just give a prompt, I'll give a prompt OX. And I'm also need to get an LX, right? Because I'm going to have to get an LX and an OX, okay? So let's just do this, and we'll add an LX equals get flow prompt. Okay, now I'm no longer getting O, right? O is LX minus OX. So I can probably just, the way I would like to do it would be O equals maybe calc O, if I like calc O, and I need for that, I need LX comma OX. So I'm starting by writing my main code. I'm not worrying about how it's done. Okay, I now have O and I have F, so I can calculate I, so there's no problem. If I can also calculate H, because I have O and I, so I can calculate both of those, so that's no problem. So I'm going to then move on to my next line. So this is, I'm going to put down add, and this was added. Okay, so I've done these 3 lines to add. So instead of getting O from the person, I'm just calculating it now. After this, I'm going to, what else do I not have? The IX. So IX equals calculate maybe IX, and what I need for that is LX and I. I have LX, right? I have I, okay? So I can just put this right at the very end. And then I'm going to want to print out my final answer, which is IX and H. So IX and H. Okay, so I've added this line, and I make a small modify. Okay, I just modify to print the IX rather than I. Okay, so that's my main program finished. Now you can see I've done 2 functions here, that I've added 2 different functions that I'm going to have to worry about. So let's do a function definition for this guy. So I'll prototype first, actually. Let's do a prototype first. I'll just copy them up here. So LX is a double, right? OX is a double. And he's returning, and O is also a double. Okay, and I've got this guy at the end. So for this function, LX is a double, I is a double, and it's returning a double. Okay, I now have function prototypes for everything. Okay, that looks good. I got function calls. Have I declared all my variables? F, H, O, I, not OX. I need OX, I need LX to declare, and I need to declare an IX. Okay, I think I've got everything declared now. So I've declared, I've initialized, use, and use. Okay, all right, so I've used them after I've initialized. Good, so I'm using LX and I, they've all been initialized first. Good. I've got my 2 prototypes, so let's take the copy of the prototypes. And we'll copy this prototype. And now we have to worry about how to do the calculation. So I want a double container. I'm going to call the double container just another O, maybe OO if I like. So OO equals LX minus OX, return OO. If I want OO, it doesn't have to be OO. I could say call whatever you like. Call me anything. I don't care. So call me my anything, whatever. Okay, so call my anything. Okay, there he is. All right, so whatever you want to call it doesn't make any difference. The other function, definition, it's going to calculate IX, so double IX if I like. I can call it something else if I want. IX equals LX plus I. And then I just return IX. So my code should, I now have function prototype, yes, for 4 functions. I've got 1, 2, 3, 4 functions, okay. So I did not touch equation lens, I do not touch C magnification at all, because once my function is working, I don't want to change it. Okay, I'm going to save it. Let's see if it compiles okay without any errors, which is my next challenge. Okay. So I'll keep it on this side, GCC minus C minus wall J dot C. It does, okay, minus C minus O J dot EXE J dot O J in lib dot O. Okay, I can now run J, input F, 4, input H, 2, input OX. Let's put it at 0. Let's put the lens at position 2. And now I just do my calculation. The image is going to be at -2. Its height is going to be at 1. All right. So we will. So at this point, we will now. I think we can probably break for about 5 minutes. Then we will do milestones. Okay. We're going to break for about 5 minutes, and at 4:30 we will start milestones.